Right, so let's have a run through on the rate equation and rates of reaction. This is specifically for revision, so I'm going to hop over things relatively quickly. So let's start with our basic equation, A plus B reacting to form product C plus D. Now we're going to make the assumption that this reaction goes to completion. There's no equilibrium here, there or anywhere at all. So our rate of reaction is going to be dependent in some way, possibly in some way at least, on A and B. And it's the concentrations of A and B that we will be considering here. But of course, we're not absolutely sure unless we do the experiment or have done the experiment, how, we're not sure how concentration of A or B will affect the rate of reaction. So therefore, we use powers to enable us to have a little bit of flexibility in saying how these are going to affect the rate of reaction. And of course, if you remember, we call these things the orders of reaction. Now, the value for these orders of reaction, well, they can be 0, 1, 2, possibly even 3. And for the syllabus that we have, of course, we generally consider 0, 1 and 2. But potentially they could be partial, they could be negative. The only way to find out is by experiment. There's something else that's missing from our rate expression here, and that is the rate constant K. Now our rate constant K, here we are, rate constant, is a constant that is temperature dependent. So as long as we keep the temperature constant, the rate constant K will remain constant. If we change concentrations, change pressure, anything, as long as we're talking about the same reaction, then the rate constant will remain constant. Very quick run through some of the basic units. Rate of reaction as units, moles per cubic decimeter per second. Concentration, generally in moles per cubic decimeter. And of course, our rate constant K will be dependent in terms of its units on the orders of reaction, the overall order of the reaction that we have in this. And X and Y are things that are going to be determined by experiment. So let's have a look at a very simple question to start off with. Here we've got a nice little question. The reaction between 2-bromo 2-methyl propane and warm aqueous 0.1 molar sodium hydroxide solution forms 2-methyl propan 2-ol. So what we've got here is CH3 3 times. So let's just have a look at the reaction. Like this, there's our bromine. And we're reacting it with hydroxide here. And we're doing simple nucleophilic substitution reaction. Replacing the bromide with hydroxide. Now, here you'll notice that the the rate expression that we have there only includes the 2-bromo 2-methyl propane and doesn't have hydroxide. So therefore, in this case, it's going to be first order with respect to the 2-bromo 2-methyl propane. So we could, if we like, have a little 1 there. And it's 0 order with respect to hydroxide. And because it's 0 order with respect to hydroxide, we leave that out of our rate expression. If it's first order, of course, generally we don't put the 1 as the indices there. It's just assumed that that's what we have. So let's have a look at the question. State what is meant by the term rate of reaction. Well, rate, don't just talk about speed or how fast a reaction goes. That's not really what we're talking about. We're talking about changing the concentration with time over change in time. Something like that. Now the units of K, of course, depend upon our rate expression. So let's just have a look and see how we can work this out. So we know that our rate is equal to K concentration of CH3 3 times CBr. I'm just going to make this a little bit bigger, if you don't mind, so that I can see what I'm doing. Let's just move it around. There we go. So we're going to state the units of the rate constant. Okay, so we've got that there. Let's rearrange that equation, shall we? So we can get K. So K is going to be equal to the rate over the concentration, like that. Now the units of rate, of course, are moles per cubic decimeter per second, and the units of concentration here are moles per cubic decimeter. So in this case, what we can see is to determine the units of K, all that we need to do is to cancel the moles per cubic decimeter at the top with the moles per cubic decimeter at the bottom, and therefore units of K are seconds to the -1. Okay, so let's just have a look at the next part now. Deduce what the effect on the rate of reaction will be if the concentration of the sodium hydroxide is increased to 0.3 moles per cubic decimeter. Well, we know here that it is zero order with respect to hydroxide. So therefore there will be no effect on the rate of reaction by changing the concentration of the hydroxide, because the hydroxide does not occur in the rate expression.